Okay, for our second talk of the day, we'll have Cong Xue, who's going to speak about giving her second talk about Shtukas.
So today we will continue yesterday's lecture. First, I will explain Benison-Grunfeld avant-Grassmannian, and then a map from stack of Shtukas to the Benison-Grunfeld avant-Grassmannian. And then I will describe and recall the geometric zeta k equivalence to associate a canonical sheaf to stack of Shtukas, then define its cohomology and try to explain the very important partial Frobenius action on the stack and on the cohomology. At the end of the talk, I'll try to just say some philosophy from the point of view of geometric Lagrange to say Shtukas and their cohomology. So continue last time, Benison-Grunfeld avant-Grassmannian. Compare yesterday at the Benison-Grunfeld, because today we will see avant-Grassmannian in family. So let's recall the classical avant-Grassmannian. That we say yesterday associated to the group G. It's the FPQC quotient of the loop group by the positive loop group, where the loop group is sometimes we write it like this. For simplified, classify the functor that I read yesterday, and positive loops classify a functor given by this. And today we will describe the avant-Grassmannian in a more rest on the functor in a more geometric way. So let R be a K algebra. So let K be a field. For example, QFQ. R commutative K algebra Grassmannian over R. It classifies a G bundle over the unit disk. We classify d'abord first so the dr means the unit this unit disk, and a modification between this G bundle and the trivial G bundle on the punctured unit disk. So this is the punctured unit disk. And we can also write it In this way, we have a modification between two G bundles and a trivialization of the second one with the trivial G bundle.
You already restricted the function disk, so why do you still write the dotted arrow?
Oh, yes, yeah. It's isomorphism. Yeah. So it's isomorphism outside the 0 point. And to say the relationship between this description and this one is that if you trivialize the two, if you trivialize G0 and G1, this isomorphism over the puncture disk give you an element in this loop group, give you an element in this, and then we quotient out the modifications of this, so you quotient out by this. And yesterday we saw that this positive loop group act on Afan-Grassmannian by the translation from left. And if you say from this, the action of this group, in fact, this group is a group of trivialization of trivial G bundle over the disk, and the action is by changing this trivialization. I will write down this. So the action of this Grassmannian is by changing this trivialization. And yesterday we saw that we have defined this subscheme in Afan-Grassmannian, the orbit of the L. A dominant covariant lambda. And in this description, so this is a notation. So in that one, so we have this. we say that so you say that this phi gives you an element in the G double quotient to say. So this phi give you some element in these things. Give you a class in this. And we say that this in this orbit means that the which means in this case, the phi corresponds really to this element, to this T lambda class. Because by definition, it is the orbit, this one. By definition, this is the orbit of this element associated to lambda. And we have said that, so in this description, this isomorphism on the punctured disk, in fact, is given by an element in this double coset. And the element in this orbit, the element is exactly this one. Yes. The trivial D. So when I use this notation, I mean a trivial bundle over this. When I said trivial bundle over something, it means a trivial bundle over this. And we also have this. Yesterday we saw that this is the Hesky closure of that thing, the Schubert variety. And in this language, we say that the relative position so sometimes you may say this sentence in the definition of bounded Shtukas, and this means that so yesterday we saw that this is the union of this the Hesky closure is a union of the orbit for a dominant covariate smaller than lambda. So in fact the phi always give you some element T mu in the double coset, and here bounded means mu smaller than lambda. Exactly the same condition here. So here means that the element correspond to this modification is some element with the weight smaller than lambda. Oh. Yes, so this is a notation means the difference is the sum of positive root. Positive co-root. A combination of positive co-root.
I think that it was objective can be taken in a form of TU, but is this also true if you put an arbitrary R? Is it true that your ring is arbitrary? Is it true that every double posit you can pick her?
I don't know. For the if you want to be sure, take be a field. Perhaps it's not precise. There are precise definition. In fact, precise definition of a G bundle over this is given by representation to a category, and the category are the vector bundles over this, and vector bundles over this are the finitely generated free module over the double coset things. So, to have we can take always take R to be a field to make yes. If not, we have to say that such that for every geometric point you have this relation. So now let I be a finite set as yesterday. When I legs. Now as a fan scheme over FQ. Yes. And in real mathematical meaning, it means in fact the pole or zero of a map, because that's where the map is not defined. So it's in fact, it's pole. So we have a coordinate of for each leg we have a map from S to X, and we have G bundles over the formal neighborhood of union of all the legs. So I use this notation. It means of union of graph and some generalization of the formal disk. And we have a chain of modifications where each phi I is isomorphism outside one graph. And we have a trivialization of the last one with the trivial G bundle over the whole thing. So it classifies the data of a chain of G bundles over this formal completion, and each time you have a modification outside one graph, like yesterday. Just yesterday we have bundles over curve. Today we have bundle over the local things. So it is it is over I copy of the curve. We can also define this one without intermediate modification. Just like yesterday for haiku. And as yesterday, we have the map from the one with intermediate modification to the one without intermediate modification. So everything are over I copy of the curve. So you send the send this to the composition of these modifications. And then to for example, when I is a synchrotron, in this time, so it is just over one copy of the curve. And we say that so it's classified just one modification. Looks like the Alpha-Grassmannian, classical Alpha-Grassmannian, and it's in fact it's fable over a point. A closed point is just the Alpha-Grassmannian. In the definition, you take be the reduced field at your point. Not replace you identify this by the with the local field at x, and this with the local field integral ring at x. However, the fiber of Benson field Alpha-Grassmannian for a finite set, which is not synchrotron, is more complicated. They are products of Alpha-Grassmannian. It depends on where those legs are the same or not. So that's what I will write down in an example. So now let's consider I a set of 2 points. So you consider the one without intermediate modification, just one and you can say that when the 2 points are not the same, the fiber is a product of 2 Alpha-Grassmannian. And when the points are the same, the fiber is just one Alpha-Grassmannian. Because this is just that you have this classified saying that you have 2 points and the modification outside the point. But when your 2 points become the same, you just make modification outside the point. So what you get is, in fact, one Alpha-Grassmannian, the fiber. And in that case, if the 2 modifications are not the same, you can say that I do an intermediate modification. You can separate the modification in 2 different points by an intermediate one. In general, fiber of this one over some point is isomorphic to product of Afan-Grassmannian, but the product is over the point view as a set, which means you only take the one which are not equal to each other. So in this case, the set is just 1 point. So like this. And now we will consider the this. So this is when x2 equal to x1. In that case, so this classify 2 points and modification outside this 2 point. And when these 2 points are equal, you just have a modification outside the point. Oh, in this case, you only have one. And remember this one is this one. Because this one, the notation is that I put all the set together, and that one I separate the things. Sorry, the notation is not quite well. I just put.
If you pass to the locus where all the points are different,
yes.
is this the position also in the focus money?
Yeah. Yes. So where all the points are different, you have the fiber is product of K copy of Afan-Grassmannian.
I mean, not only fiber, global side.
Yes. Yeah. Oh.
Yes, one leg. I probably got that. But maybe also understand the question, but I mean, for the bracket line, the farmer's money is not as equal to the local farmer's line in half of the farm. But still, the government is a part. Yeah. The individual package of this month. Yes.
I will write down something perhaps help. So let this be the open in xi. Which is where all the points are different. Like we saw yesterday, where all the legs are different. And over this, this one, it's isomorphic to the product of of this So here, this notation means Bennington Dreamfield Grassmannian with one leg, and the leg is this one indexed by I. So this is this over X, and the copy is over Xi, and I restricted it to the open. So over the open, the fiber of this is this, and the fiber of the lower one is also this. So the fiber of this map over the open, where all the legs are different, is isomorphism. And sorry, I will use this part. And now let lambda be a dominant coed always. We define first we define so when I is the singleton, in this case, we see that the fiber is just one copy of Affine Grassmannian. So we defined this to be that each fiber is in this orbit. Yes, in fact, this is a fibration over X. When the fiber the Grassmannian, and when the torsor it's a torsor of automorphism of the former disk, so we can define the this condition. And now when there are several copies of in general case, for this one, we define first we defined it only over the disjoint open, the open of this one. Over this, we defined it to be the product in fact, what we are really interested is smaller than lambda, because this one is a proper, is the Hesky closure of the lambda. So this one is projective. We prefer to work on this one. So on the open, we defined it as a product, and then we take the Hesketh closure of this. Of this. And similarly, we can define the smaller than lambda for this one by the same way. First, we define over this, and then we take the closure, or we take the direct image by, or we take the image by this one. They are the same. So now we define this. They are projective schemes with finite dimension.
G1.
Yeah.
Where is it live? So is it those something where?
It's this one. This one. So inside there is this. Inside this one, you have, I defined this closed subscheme.
What confuses me, there's no upper index.
Oh, because there is only one, like the different upper index to be the same. So I didn't write. Yes, we can put an upper index. Oh, sorry about my notation. Because when there is only one, like I just didn't put upper index. Yes, I should write index. I forgot. And in fact, when there is this map is small. For who want to know. And now let's look at the action of the group. I say it is a small morphism, which means that like a semi-small morphism with the condition more strictly. So when you consider the stratification to define the power shifts, this means the stat have the good dimension. You don't really need to know what it means. It's a morphism which is very good, such that the some kind of your IC shift, your complex intersection on the top. If when you take direct image, you get an intersection complex on the lower thing. So, just forgot if you want. We also have the family over the curve of the loop group. So this one, it's some kind of, it's classified point, and it is a group of automorphisms. Of the trivial G tensor over the formal completion of union of all the graphs. So this is a family version of loop group. It acts on Bennigsen field Afan-Grassmannian. Any of this one. By changing the trivialization. Yes, so the action is by change this thing. This thing. This they are stable by the action of, because in the Afan-Grassmannian classical case they are union of orbit, so they are stable under the action of the family version. Excuse me. Oh no, I said it acts on both. It acts on both of these by changing trivializations. And now we can define our map from Shtukas to Afan-Grassmannian. So we have a map from haiku stack. Not exactly to the Bennigsen field Afan-Grassmannian, but cautioned out the action of this group. So this, you see that this is classified a chain of modification with a trivialization. So it classifies these things, and the action of the positive loop group is by changing this trivialization. So if you cautioned out the action of this, you just classify these things. You don't have this trivialization. The map so these are G tossers over x times s yesterday. I sent this to the restriction to the formal completion of all the graphs. You see that this one is classified just modifications, but not the trivialization of the last one because we cautioned out this action. No, not at all. Not at all, because these are you need a boundary. And we have a map from Shtukas to Haike. Yesterday we saw the definition. It is we send Shtukas to Haike. We just forget the forbiddenness. It's a special case of Haike. So we get this map. Recall that yeah. Yeah. Oh, this means the restriction. Oh, it is not trivial. We don't have trivialization because you cautioned out this group.
It still exists some. You know, you get it.
Yes.
But all the part that the scheme is complete on the add-on scheme. I almost think so. I didn't realize it's probably. That's part of this amendment. It changes totally must keep it by the town policy in this policy. Right?
Yes.
Otherwise.
Yes, so Shtukas classify these things and you send it to Haike. Just you send this to this. Your last one is this. So this is a composition of these two maps. Yes.
Because say like there's also a point in there. So if let's say I put a field in there. So am I gonna get a point in xi as part of the data? I understand that fiber-wise I should get automorphism.
Yeah.
But I don't understand the definition.
Oh, perhaps this is not the good definition. Sorry. I just want to mean that I just want to define a global family version of the positive loop group. Perhaps precisely is not like.
But so what's the identity element shouldn't then single out the point?
It's a section. It's a group's relative. It's only right to be honest. Only relative.
Okay,
Section.
And this map, the fact is that this map is formally smooth. and we
It's more like a pump. Maybe more even volume when you pull back. Sorry.
and we define this bounded version of Shtukas to be the inverse image of the bounded version of Benison-Drinfeld Affine-Grassmann. And the now we get a finite dimensional things. So now this is the linear Mumford algebraic stack locally of finite type. You can do everything with another decoration. You can consider the not iterated Shtukas and get defend the similar things. And usually it is not smooth. Perhaps I'll just example of smooth one, Drinfeld Shtukas. So it is for GLN when it's a special case when there are two legs, and for the first leg you take this COVID. For the second leg you take this COVID. Sorry. In the definition of this one, yes, I'm really sorry. In this one, you can take a triple of this. And for yes, for this one, you can have different, of course, different co-weight for different copies. Different legs can have different copies. Yeah, G is GLN. So in this case, you have 2 points, And in GLN case, your G tosser is it classifies rank n vector bundle. So you have a vector bundle, and this now the dotted point, I can write it really as a map, but it is not defined overall. We have phi 1, phi 2. And the condition is that, so this is a lower modification. The modification is, so they are isomorphism outside the first leg. The modification is only on the first leg, and we do a minimum modification on this leg. So the quotient is supported on is a skyscraper sheaf supported on the graph of the first leg, and on the invertible sheaf. So they are isomorphism outside the first leg. The difference on the first leg, the quotient is an invertible sheaf on the first leg. And for this modification, it is support on second leg. So yes, of course. Phi is an isomorphism outside the graph. That's why the quotient is only the quotient is a skyscraper sheaf support on this.
The one alarm that you have as a special form.
This means that because this is in this, and this lambda means that this quotient you have longer 1, and this quotient you have longer minus 1, and the element you give in the matrix is something like this. There are some dictionary to write down this one. Because this lambda in the GL1 case, it corresponds to an element like this in GLN this locally, and if you write down how to say.
Yeah, so if I replace this 1 by 2, so what would change?
This become if you change 1 by 2, this is not invertible sheaf, it's a sheaf of rank 2. Perhaps you need some more condition. And so one means we do a modification, such that the quotient is of rank 1. So I just use the last time to explain why we are interested in this stack of Shtukas. So why we invented this strange form of things. Take this one. Now it is a finite dimensional scheme over copy of curve. We are interested in the cohomology of compact support. Of its IC shift. It has the intersection complex. Because UUN8 is not smooth. When it is smooth, IC shift is just the constant shift shifted by some degree. And in particular, in the case of Drinfield's Shtuka, the stack is smooth because you have minuscule co-weight. So in Drinfield's paper, he used cohomology with coefficient in QL because his stack is smooth. And in general, we have to consider cohomology with coefficient in intersection complex. It's what we use to study no smooth varieties. And we consider cohomology with compact support, which is a direct image of this IC shift. And on the cohomology, we have action of Haeckel algebra given by Haeckel correspondence, as what you saw in the first lecture this morning, given by Haeckel correspondence. And also there are action of, oh, sorry, I forgot to say we chose the generic point. And a geometric point over the generic point. So we consider cohomology on the restriction to the geometric generic point. So on this, it has the action of the pi1 of this generic point. And it has action of partial Frobenius. Which unfortunately I don't have time to say. It's something like you send a Shtuka you send this one to another one, and you put this part here. So this part you keep, but this part you put it here, but you put Frobenius on everything. And this the good thing is that, so this is Frobenius for first leg. If you repeat these things k times, then you can do this for 2. And the thing is that if you at the end, you will get the Frobenius of the original things, which means first you get the And first you find Frobenius of this, and then Frobenius of this, and then Frobenius of this. At the end, you get Frobenius of the total space. Usually we can't write Frobenius of total space as some product, but here you can. And the thing is that the cohomology of this, since it's direct image, it's also sent. The cohomology is also you put this to this and to this, and in fact they are not really the same space of Shtukas, but a kind of difference. But since they are all how to say. The cohomology didn't depend on the intermediate modification or not intermediate modification, because the image of your IC shift here, direct image on this is the IC shift of this one. And we have a more precise formula to state this. It's enough to define cohomology, use this space. We introduce this to define partial Frobenius, because you can only define partial Frobenius with these intermediate modifications. The reason why we want this is that these two things together by Drinfield's lemma, give you an action of V group of the function field power I on the cohomology. That's why. So now we are related this cohomology with the function field. We are interested in Galois group of the function field. Here V group is a V group in Galois group. That's what we I is this index, the curve. And yes, in fact, we need to use the geometric Sadake equivalence to make this definition more precisely, and use, in fact, the representation of the dual group of G. I think I should say at the answer, the dual group of G. And in fact, for any representation of the I copy of the dual group, we have a cohomology indexed by this representation, which is functorial, have many good properties. And when this representation is irreducible, when it's irreducible, it's a product of irreducible representation indexed by highest weight of the dual group, so highest co-weight of, so a co-weight of the group. That's why you relate to this, to this. So this is a very special case of W. And in general, we have a cohomology of like this. And use this. How to say? So the work of Vincent Lafforgue is that he used this cohomology group to define the excursion operator on the space of automorphic forms. You have space of automorphic forms. They are the function on FQ point of Bangji. And in fact, they are equal to the cohomology group with empty leg. And in fact, you can relate to the cohomology with empty leg to the cohomology with arbitrary leg you want. And then you make action of this V group. You make action of this V group. And then you go back to the cohomology without legs. So he used this to construct some operator on the space of automorphic forms, which generalize the Haiku operator. And he used this operator to get a decomposition of the Caspito automorphic forms indexed by the representation, indexed by the Galois representation. The representation from a group of Galois function fields to the dual group of G. So that's why, what? It's a representation of I copy of the dual group. It's a QL linear representation of I copy of the group. So this is some general form of the cohomology of, so this should be generalized to this. Generalized to this one using the dual group. Could I say 2 more minutes? Sorry, I just take 2 more minutes to tell you some another point of view from geometric Lagrange. So it is very philosophically. So geometric Lagrange on the automorphic set, they have the Bangji stack. They consider the category of and scheme of the unconstructible sheaf on Bangji with support on nilpotent. So every stack is DG stack. Every category is infinite category something. And they have conjecture equivalence between this and the Lagrange set. Some local system relate to G height. Category of uncoherent sheaf with nilpotent support. And they also have now a theorem is that if you take trace of category, so of the Frobenius, there is some so they defined so usually if you have a sheaf on a variety, you take trace, you get function on the FQ point of the variety, and they have they take trace of the category of sheaves, and they get a vector space at the end. So this is a vector space. This is the automorphic. This is function on FQ point of Bangji. And if here you consider some kind of action of Haiku associated to I and W as there, composed with the Frobenius action. you get the cohomology of Shtukas. Because so this yes, because what happens to the space of stack is here you get the graph of Frobenius, so the FQ point of Bonji, and here you get it here on what happened on the stack. You get the definition of Shtukas, the fiber product of Haiku and Bonji. This is some notation, perhaps bad notation. I just want to say that in fact the cohomology of Shtukas you can recover from this way. So these are theorems. And then they take a trace of this side, they get some this and this will give you some something more better than decomposition of Lagrange. Yes. Oh, sorry, I forgot to tell you the references. So references for this is a serious paper written by these authors. So they have at least three papers around 2000 and 2000 no, and they have 3 papers around these things. And for the other part of the Shtukas, you can see the EHS summer school lectures last year. So in Ziwei Yun's talk, there you can see all what I said today, and the relation of Shtukas to Drinfield's module, if you are interested, and a lecture of Winston, which if you want to know relation of Shtukas to periodic geometry, and there are also lecture of Sam Haskin about this subject. So I think I stopped. And also my lecture about more things on cohomology.